We have the
There's more.
IOCCC prize in patient pointillism, which I can only imagine is somebody staring at a dot on their screen until inspiration strikes.
It is an inspired piece of code that you have to be patient with.
Okay.
There's a point to it.
Okay.
But let's see who won this prize, because they've been patiently waiting to see, will their submission win?
Absolutely.
And now,
I will press the
without
button.
further ado,
I'm going to press it.
You have to be patient.
In now.
And the IOCCC prize in patient pointillism goes to Yusuke Endo from Japan.
Well done, Mr. Endo. This is a world record 19th IOCCC contest win. It is a very impressive piece of code. As you see, Yusuke Endo is a prolific Obfuscated C coder. And if you look over his portfolio, you find an extraordinary wide variety of submissions. We judge it anonymously, and so this was one that I had no idea, in what style it was. He comes through with an amazing piece of code, and I want to show you, first of all, how to compile it. So here's what you do. You compile the program, pretty straightforward, and you run it, and it produces this source code called rt.c. Okay, that's what you do. The code itself comes with this makefile, and the magic here is in this makefile, where it's doing a bunch of targets over and over again, running the compiler, specifically the C preprocessor phase of the compiler on RT for every one of these targets. Say, what? What could this possibly be doing? So here is the source code. It is not clear what's going on, but if you start seeing things like including __ file __, and other things, you know you're in for a good time, because the output is going to have a piece of street code that's going to include itself in some very creative ways. So this is again, understand, this is the code to produce rt.c, which we're going to compile over and over and over and over again. To do what? Well, let's look at what rt.c looks like. And you see it's a bunch of loops, a bunch of powers of 2. It's got some other defined variables. Eventually you'll see in there highlighted an include of itself deep into its guts, and other loops unrolling. There's actually another inclusion of itself a little bit later on, and some more loop unrolling to terminate to the end. That's rt.c. So his program produces rt.c, which we're going to then compile. And by the way, this is the thing that there's the Z, which does sort of the stuff as well. It's a fun piece of code that it produces. So again, looking at what this does, you can see that's got a bunch of defines. It's got these code blocks there that are rather intricate. And so this is an example where it will build an 8x8. So let's stop here in a moment. So what it did is it built an 8x8 ppm, basically a colored image, where every pixel was a compile CPU process of rt.c. But what it does is you tell the CPU processor your X and Y pixel and the size, and it goes through and computes what should be the red, green, and blue value. It's putting on a ppm where it starts off, says, okay, I got an 8x8 and the maximum thing is 255, and then I produce in parallel. So what you saw was sped up on a 6-core machine, all of these things, and it took it about 12 seconds to do all that. Again, RT.C is running it. So let's go to the next one, the 16 by 16, and see what it does. I think I can do it there. Yes. And here we see that whoops, I'll go back to the previous one. Back again for this. That's the 8x8. And then there is the 16 by 16. And we see 16 by 16 again, where here we're saying, here's a 16 by 16 size. It goes through all the pixels, so 16 squared. So this takes about 5 minutes to produce a 16 by 16 image, where the point of RT.C is to produce a red-green pixel value of a single point. If you look at 32 by 32, again, it's going to do it 32 squared and so forth. In fact, if you go on bigger and bigger, you'll find, for example, 128 by 128 takes roughly 87 minutes to do all the compiling. If you do it in if you do it as a 512 by 512 image, it on a single core, this is actually running on 6-core machine. So the 512 by 512 image on a 6-core machine took almost a day of compiling each for each particular pixel. It's a pretty extraordinary stuff. So what does it do? Well, here is what you see. So on the far left is the 8x8 image. The next one is the 30 by 32 version. The next one's 120 by 128, and the next one's 512 by 512. So to really appreciate what's happening here, RT.C, which is generated by prog.c, given the defines on the command line, will go through and do all of the ray tracing, all of the reflection necessary and shading for a single pixel. And it'll do it. You can do images up to about, we think the maximum size is 2 to the 31st minus 1. And if you were to try to do an image that size on a single core, it would take about 169 billion years. So we don't recommend you try something that big. But there is by the way, you can do some parameter changes. So this is an example of an image with a different set of parameters to sort of change some of the shading of stuff. And again, the same RT.C, the CP processor, remember, this is a CP processor doing in CP processor the ray tracing, shading, color stuff to do what? To get one pixel, they have to do over and over and over again, very patiently. It is an extraordinary bit of code. So we have a challenge. Where someone say, can you do a image larger than 512 by 512, which took a 6-core machine about a day? And if you are the first person to render a new record size image, we will honor you by putting you into the thanks file on our webpage. You tell us the size and the URL of the image, how long it took. And again, please keep faithful to Yosuke Endo's spirit of the algorithm, but tell us how you were optimized, what kind of parallelism you did, and let's see how big of an image we can make with this patient piece of code.
Absolutely, and I'm sure that the next winner of the next category has also been patiently waiting to find out if they've won. So we should.
But well done. I was very impressed with this piece of code. It was.
It's really.
We've had. Go ahead, David. You do graphic stuff.
Yeah. I specifically spend money to make things go faster, though. Right, this would be, I would Control Alt Delete myself if I had to render this way for everything. Yeah.
Yes. But it's a
it's-
master.
It is very clever,
master
though.
Yes. I mean, we had early on, we had a deployment who did a prime number sieve in the C processor. This goes a step further and determine the pixel of a given image through the algorithm, and the shading and so forth is all contained within that set. Well done. Thanks for watching. And before you go, please like and subscribe and check out the social media links in the description below. And if you like, you can support us on Patreon to help us bring you new content so you may enjoy our favorite universe even more.